Okay, setting up and solving differential equations part 5. Make sure you've watched the previous ones. A sample of a radioactive isotope of radium loses half of its radioactive nuclei each 1200 years. That is, its half-life is 1200 years. Yeah, for those of us who haven't done physics before or talked about half-life before, it just means that you start with a certain amount. Here's our certain amount. After 1200 years, you have half of that amount. After 1200 years, you have half of that amount. After 1200 years, you have half of that amount. The equation is going to be what's called a decay curve. Okay. If the rate of decay is proportional to the number of atoms present, find to the nearest year the time taken for the isotope to decay to 30% of its original amount. Okay, so it's not going to be 1200 years, but it's going to be less than 2,400 years, because by 2,400 years you'd have 25%. So at least I have a ballpark to work with. Now we can write this as, so the rate of decay is proportional to the number of atoms present. So the change in the number of atoms, which I guess will be n, with respect to time, is going to be equal to, if the rate of decay is proportional to the number of atoms present. So it's going to be equal to K number of atoms present. Okay, so if we let n be the number of nuclei present at any time and let n0 be the original number of nuclei, we'll get an equation of dn dt equals Kn. There we are here. And then we can start solving that in the way that we've always done it. So we can invert that equation, dt dn. We can express in integral form, t equals 1 on k, integral dn on n plus c. So they've just taken the 1 on k outside as a multiple. And to differentiate that by rule, so you should be able to tell me that that's t equals 1 on k log base e an, and that a has come from that c, and I've spoken about that a few times. Again, come and talk to me if you need to. Now, we've got our n here, and we still want to know what a is. Now, this is a sneaky one because we don't really have an initial condition so much. So that's why up the top here, they've done this little bit here where they say let n0 be the original number of nuclei. So we're just going to sub n0 in for n when time is equal to 0. Let's do that here. When time equals 0, n equals 0, an0 equals 1, which means that n0 equals, or a equals 1 on n0. So if we sub 1 on n0 in for a, we'll get t equals 1 on k log base e n on n0. So I'm just subbing in that for a there. See, there's a there, there's n0 there. But we can then do t and n. We do have some number here, I believe. If the rate of decay is proportional to the number of atoms present, okay. So, okay, at time 1200, so after 1200 years, n is going to be equal to 0.5 n0. N is going to be equal to 0.05 n0. Okay, so when t equals 1200, n equals 0.05 n0. 1200 equals 1 on k log base e 0.5 n0 over n0, and those n0s are sort of going to cancel out here. And so we can solve and find that 1 on k equals negative 1731.234, and we can sub that back into our original, I should say sub that back into our original equation there, which gives us t equals negative 1731 log base e n on n0. Now, let's go back to our question here. If the rate of decay is proportional, find to the nearest year the time taken for the isotope to decay to 30% of its original amount. So if we leave t as the subject here, and we want to go to 30% of our original amount, we want to make n 0.3 of n0. N equals 0.3 of n0, and we sub that in here. So t equals this, 0.3 n0 over n0. The n0s are going to cancel out again. So it's going to take 2084.359. So a little less than 2400, which is what I suggested at the beginning, because 2400 would have been 25%. All right, so a little bit of sneakiness here, but it's if I don't have a known original number of nuclei or a known original number, then I can let it be n0. And throughout our process, as long as we have some multiple of n0, a half, 30%, then we can put those known multiples of n0 into our equation, and those multiples of n0 cancel out, and we're left with something nice and neat. Okay, quite a bit there, but it's really just a twist on what we've already done. If you don't know the original amount, but the question refers to multiples of that amount, then you can still do your equations.